Billions of years before our solar system twinkled in the cosmos, they were already there, ancient stellar cities hanging in the void, defying the relentless march of time. These are globular clusters, gravitational ballet troupes of ancient stars, their stories etched in the fabric of the universe. Imagine, if you will, a single globular cluster as a celestial time capsule, a relic from the universe's infancy, holding secrets of our cosmic past. In the vast, ever-changing theater of the cosmos, these clusters stand as enduring monuments, their stars like ancient sentinels, whispering tales of the universe's earliest days. Join us as we journey to these ancient stellar cities, where each star is a storyteller, and every cluster, a library of cosmic history. The celestial tapestry, a glimpse into the cosmos. In the vast, velvety expanse of the cosmos, globular clusters stand as ancient stellar cities, their twinkling inhabitants bound together by gravity and time. These spherical conglomerations of stars, often numbering in the hundreds of thousands, are among the oldest objects in the universe. Their age is staggering, with some estimates suggesting they formed around the same time as the galaxies themselves, over 13 billion years ago. This makes them veritable relics, silent witnesses to the evolution of the cosmos. Each star within a globular cluster is a sun, much like our own, yet their collective dance is a spectacle unlike any other. The stars are packed tightly together, their celestial ballet choreographed by the invisible hand of gravity. This proximity gives globular clusters their distinctive, densely populated appearance, a stark contrast to the more sparsely inhabited spiral arms of galaxies. The light from these ancient stars, though faint to our eyes, is a testament to their endurance, a beacon of resilience that has withstood the relentless march of time. The Milky Way alone is home to around 150 globular clusters, each with its own unique story to tell. One of the most famous is Omega Centauri, a behemoth containing several million stars. It's so massive that some astronomers believe it might be the core of a dwarf galaxy, stripped of its outer stars by the Milky Way's gravitational pull. Another notable cluster is 47 Tucanae, the second brightest globular cluster in the night sky. It's a favorite among astronomers for its relatively close proximity and the wealth of information it provides about the early universe. Globular clusters are more than just beautiful celestial objects. They're treasure troves of scientific data. By studying their stars, astronomers can gain insights into the early universe, the formation of galaxies, and even the nature of dark matter. The stars in these clusters are often low in heavy elements, a sign of their ancient origins. They formed from the pristine material that existed shortly after the Big Bang, before successive generations of stars had a chance to enrich the cosmos with heavier elements. This makes them invaluable windows into the past, offering a glimpse into the cosmos as it was in its infancy. Ancient marvels, the birth of globular clusters. In the vast, dark expanse of the cosmos, globular clusters stand as ancient stellar cities, their origins shrouded in the mists of time. These spherical conglomerations of stars, tightly bound by gravity, are among the oldest inhabitants of the universe. Born in the early epochs of galaxy formation, they are relics of a bygone era, their stars forged from the pristine material that emerged shortly after the Big Bang. Their age is staggering, with the oldest known globular clusters being nearly as old as the universe itself, a testament to their remarkable endurance. The birth of these ancient marvels is a tale of cosmic drama and stellar nursery chaos. Unlike their younger, more organized cousins, open clusters, globular clusters formed in a frenzy of star formation, triggered by the violent collisions and mergers of primordial gas clouds. These clusters are characterized by their high stellar density and spherical symmetry, a result of the intense gravitational interactions that shape them. The stars within them are often ancient, metal-poor, and populate the galactic halo, orbiting the galactic center in a vast, spherical distribution. This distribution is a clue to their origin, suggesting they formed before the galactic disk took shape. One fascinating aspect of globular clusters is their role as stellar laboratories. They offer astronomers a unique window into the early universe, providing insights into the processes that governed star formation and galaxy evolution in the past. The stars within these clusters are like cosmic fossils, preserving the conditions and compositions of the early universe. For instance, the study of globular clusters has revealed that they often host multiple stellar populations, with stars of different ages and chemical compositions. This is a puzzle that continues to challenge our understanding of star formation and cluster evolution. Moreover, globular clusters are not just ancient, they are also incredibly resilient. They have survived for billions of years, enduring the gravitational tugs and pulls of their galactic hosts, as well as the explosive deaths of their most massive stars. Some have even been found to host black holes at their centers, a testament to their ability to retain the remnants of their most massive stars. This resilience makes them invaluable tools for studying the long-term evolution of stellar systems. For example, the study of globular clusters has provided evidence for the existence of intermediate mass black holes, a type of black hole that has been notoriously difficult to detect. Stellar metropolis, the structure of globular clusters. In the vast, dark expanse of the cosmos, globular clusters stand as ancient stellar cities, their structures a testament to endurance and timeless beauty. These spherical collections of stars, tightly bound by gravity, are among the oldest inhabitants of galaxies, their ages rivaling the universe itself. Their dense cores and sparse outer regions create a striking contrast, a celestial ballet of stars that have danced together for billions of years. The structure of a globular cluster is a marvel of nature, a cosmic metropolis where stars are packed closely together, their interactions shaping the cluster's evolution. At the heart of a globular cluster lies its dense core, a region where stars are so closely packed that they appear to merge into a single, luminous body. This core is the cluster's gravitational well, where the pull of stars upon one another is strongest. Surrounding the core is a gradual tapering of stellar density, a gradual lessening of the cluster's embrace. The outer regions, or halo, are sparsely populated, with stars drifting like lonely sentinels in the cluster's gravitational field. This structure is not static, it evolves over time, shaped by the relentless dance of stars within the cluster. The stars within a globular cluster are not uniform. They vary in mass, age, and stage of evolution. Yet, they share a common origin, born from a single giant molecular cloud that collapsed under its own gravity. This shared heritage gives globular clusters their distinctive appearance, a spherical shape that sets them apart from the irregular forms of open clusters. The stars in a globular cluster are also remarkably metal-poor, a term astronomers use to describe stars with a low abundance of elements heavier than hydrogen and helium. This is a clue to their ancient origin, for they formed in an era when the universe was still young and the heavier elements had not yet been forged in significant quantities. The structure of globular clusters is not just a matter of aesthetics. It plays a crucial role in their survival. The dense core provides a gravitational anchor, preventing the cluster from dispersing into the galaxy. Yet, this density also leads to a phenomenon known as dynamical friction, where stars lose energy to their surroundings and sink towards the core. This can lead to the formation of binary star systems, where two stars orbit a common center of mass. These binaries can then interact with other stars, leading to a complex dance of stellar interactions that can ultimately lead to the ejection of stars from the cluster. This process, known as evaporation, is a slow but inevitable part of a globular cluster's life cycle. Despite this, globular clusters are remarkably resilient, their ancient structures enduring for billions of years. They are, in a sense, the cities of the cosmos, their structures a testament to the enduring power of gravity and the timeless dance of stars. A dance of stars, the dynamics within clusters. Globular clusters, those ancient stellar cities, are among the oldest inhabitants of our galaxy. They are densely packed collections of stars, bound together by gravity, and their age is staggering. Some of these clusters are nearly as old as the universe itself, forming just a few 100 million years after the Big Bang. This makes them invaluable fossils, offering insights into the early universe. Their endurance is equally remarkable, having withstood the relentless passage of time and the gravitational tug-of-war within the Milky Way. Within these clusters, stars engage in a mesmerizing dance, a ballet of celestial bodies. The dynamics are complex, governed by the laws of gravity and the initial conditions of the cluster's formation. Stars orbit the cluster's center of mass, their paths influenced by the gravitational pull of their neighbors. This results in an intricate web of interactions, with stars constantly deflecting each other's trajectories. Over time, these interactions cause the cluster to evolve, with stars migrating towards the center or being ejected into the vastness of space. This process, known as dynamical evolution, can take billions of years, further emphasizing the endurance of these stellar cities. The dance of stars within globular clusters is not merely a spectacle, it's a survival strategy. In the dense cores of these clusters, stars are packed so closely that they can actually collide or merge. These stellar encounters can lead to the formation of exotic objects like blue stragglers, which appear younger and bluer than their counterparts due to their rejuvenated appearance after a stellar collision. Moreover, the gravitational interactions can also lead to the formation of low-mass T-ray binaries, where a neutron star or black hole strips material from a companion star, emitting T-rays in the process. These phenomena make globular clusters natural laboratories for studying stellar interactions and evolution. Interestingly, the dance of stars within globular clusters can also lead to the formation of multiple stellar populations. Initially, it was thought that all stars within a globular cluster formed at the same time from the same material. However, recent observations have revealed that many clusters host multiple generations of stars, each with distinct chemical compositions. This suggests that the dance of stars within these clusters is not just a physical process, but also a chemical one, with stars enriching their surroundings with heavy elements, which are then incorporated into the next generation of stars. This adds another layer of complexity to the dynamics within these ancient stellar cities, making them even more fascinating to study. The celestial time capsule, age and composition. Globular clusters, those ancient stellar cities suspended in the velvet expanse of the cosmos, are among the oldest inhabitants of our universe. They are relics of a bygone era. They're stars born in a time when the universe was young, perhaps even before galaxies as we know them had truly formed. These dense, spherical collections of stars are like celestial time capsules, encapsulating the primordial composition of the early universe. Their age is staggering, with the oldest known globular clusters being nearly as old as the universe itself, estimated to be around 13 billion years old. This makes them some of the most enduring structures in the cosmos, silent witnesses to the evolution of the universe. The composition of globular clusters is as fascinating as their age. They are primarily composed of old, population-second stars, which are metal-poor, meaning they have a low content of elements heavier than hydrogen and helium. This scarcity of metals is a testament to their ancient origin, as these heavier elements were forged in the cores of stars and scattered throughout the universe by supernovae explosions over billions of years. The stars within a globular cluster are also notable for their uniformity. They share similar ages, compositions, and motions, suggesting they all formed from the same giant molecular cloud. This uniformity is a stark contrast to the diverse stellar populations found in the disks of galaxies like our own Milky Way. One of the most intriguing aspects of globular clusters is their resilience. Despite their advanced age, these stellar cities have endured the test of time, their stars tightly bound by gravity in a cosmic dance that has persisted for eons. The density of stars in the core of a globular cluster can be up to 1 million times greater than in the neighborhood of our Sun. This high density leads to a phenomenon known as dynamical evolution, where stars interact with each other, exchange energy, and even get ejected from the cluster. Yet, despite these dynamic interactions, globular clusters have managed to maintain their structural integrity, a testament to their robust formation and the enduring nature of gravity. The study of globular clusters offers a window into the past, providing astronomers with valuable insights into the early universe. Their age and composition serve as a fossil record, preserving the conditions and processes that prevailed during their formation. Moreover, globular clusters are not just historical artifacts. They continue to play an active role in the evolution of galaxies. They can be found orbiting the centers of galaxies, their stars contributing to the overall stellar population and influencing galactic dynamics. In this way, globular clusters are not just ancient relics, but also active participants in the ongoing saga of the cosmos. Their enduring presence serves as a reminder of the universe's vast timescales and the intricate interplay of forces that shape its evolution. The cosmic forge, formation of stars and clusters. In the vast, dark expanses of the cosmos, globular clusters stand as ancient stellar cities, their stars bound together by gravity, whispering tales of the universe's infancy. These clusters are among the oldest inhabitants of galaxies, their stars forging elements in their cores, much like a cosmic forge. The formation of stars in these clusters is a testament to the endurance of the universe, a process that has been repeating for billions of years. Stars in globular clusters are typically very old, with ages ranging from 10 to 13 billion years, making them some of the earliest objects in the universe. Their formation is a complex dance of physics and chemistry, a symphony of gravitational forces and nuclear reactions. The process begins in vast clouds of molecular hydrogen and helium, remnants of the early universe. These clouds, known as giant molecular clouds, are the nurseries of star formation. Gravity pulls the gas together, causing it to collapse and heat up. As the gas becomes denser, it fragments into smaller clumps, each destined to become a star. In the heart of these clumps, temperatures and pressures become so intense that nuclear fusion ignites, marking the birth of a new star. This process is not a gentle one. It's a violent, tumultuous event that shapes the future of the cluster. The stars that form in these clusters are typically very close together, their proximity a testament to the density of the original molecular cloud. One fascinating aspect of star formation in globular clusters is the process of dynamical interactions. In the dense environments of these clusters, stars can come close enough to each other to interact gravitationally. This can lead to the formation of binary or multiple star systems, where two or more stars orbit a common center of mass. These interactions can also lead to the formation of exotic objects like blue stragglers, stars that appear younger and more massive than the other stars in the cluster. They are thought to form from the merger of two smaller stars or the transfer of mass from one star to another. This process is a reminder of the dynamic and ever-changing nature of globular clusters, a stark contrast to their ancient and seemingly unchanging appearance. The stars in globular clusters are also notable for their uniformity. Unlike the diverse stellar populations in the galactic disk, stars in globular clusters are typically similar in age and chemical composition. This uniformity is a result of their shared origin, a testament to the homogeneity of the early universe. However, recent observations have challenged this view, revealing subtle variations in the chemical compositions of stars within the same cluster. These variations, known as multiple stellar populations, are a topic of ongoing research, a puzzle that astronomers are still trying to solve. They hint at a more complex formation history for globular clusters, a history that may involve multiple generations of star formation. This complexity adds a layer of intrigue to these ancient stellar cities, a reminder that even the oldest objects in the universe still hold secrets. The celestial guardians, role of globular clusters in galaxies. In the vast, dark expanses of the cosmos, globular clusters stand as ancient sentinels, their stars bound together by gravity in a celestial dance that has endured for billions of years. These spherical groupings of stars, often found in the halo of galaxies, are among the oldest objects in the universe. Their age and endurance make them invaluable to astronomers, offering a window into the early epochs of galactic formation. Each cluster can contain hundreds of thousands, or even millions, of stars, all tightly packed together in a region that might be only a few dozen light-years across. This density makes them some of the most visually stunning and scientifically intriguing objects in the night sky. The role of globular clusters in galaxies is multifaceted and profound. They act as celestial guardians, preserving the ancient history of their host galaxies. Their stars, formed from the same primordial material, share a common age and composition, providing a fossil record of the early universe. This uniformity allows astronomers to study the chemical evolution of galaxies and the processes that led to the formation of the first stars. Additionally, globular clusters can influence the dynamics of their host galaxies. Their gravitational pull can affect the distribution of dark matter and the overall structure of the galaxy. In some cases, they may even trigger the formation of new stars by compressing interstellar gas. One of the most fascinating aspects of globular clusters is their resilience. Despite the immense gravitational forces at play, these clusters have managed to survive for billions of years. Their stars are tightly bound, resisting the tidal forces that might otherwise tear them apart. This resilience is a testament to the strength of gravity and the stability of these ancient stellar cities. Moreover, globular clusters are not static, they evolve over time. Stars within them can collide or merge, creating new and exotic objects like blue stragglers, which appear younger and bluer than their counterparts. These interactions add a dynamic element to the otherwise serene appearance of globular clusters. The study of globular clusters has also led to some intriguing discoveries. For instance, some clusters contain stars that are surprisingly rich in heavy elements, suggesting that they formed from material enriched by previous generations of stars. This challenges the traditional view of globular clusters as simple, uniform systems. Furthermore, the presence of intermediate mass black holes in some globular clusters has been a topic of intense debate. These black holes, if they exist, could have a significant impact on the dynamics of the cluster and the evolution of its stars. The ongoing research into these enigmatic objects continues to push the boundaries of our understanding of the universe. The celestial cartographers, mapping globular clusters. In the vast, velvet expanse of the night sky, ancient stellar cities quietly endure, their secrets whispered in the language of light. These are the globular clusters, gravitationally bound congregations of stars that have danced together since the dawn of time. Among the most ancient of these celestial bodies, the globular clusters are relics of the early universe, their stars often as old as the cosmos itself. Their endurance is a testament to their resilience, having weathered billions of years of cosmic evolution. Mapping these ancient stellar cities is a task undertaken by celestial cartographers, modern-day astronomers who chart the heavens with an array of sophisticated tools. The process begins with telescopes, both ground-based and spaceborne, which capture the faint, ancient light of these distant clusters. The Hubble Space Telescope, for instance, has been instrumental in providing high-resolution images of globular clusters, revealing their intricate structures and stellar populations. These images are then analyzed using advanced computational techniques, allowing astronomers to measure the cluster's sizes, shapes, and stellar densities. One of the most fascinating aspects of globular clusters is their universality. They are found in nearly all galaxies, from the smallest dwarf galaxies to the largest giants. Our own Milky Way, for example, is home to around 150 globular clusters, each containing tens of thousands to millions of stars. These clusters are not randomly distributed, but are instead concentrated towards the galactic center, hinting at their role in the formation and evolution of galaxies. Their ancient stars, often devoid of heavy elements, provide a window into the early universe, offering clues about the processes that gave birth to the first stars and galaxies. The study of globular clusters is not merely an academic exercise. It has practical implications for our understanding of stellar evolution, galaxy formation, and the overall structure of the universe. For instance, the age of globular clusters can be used to constrain the age of the universe itself. Moreover, their unique stellar populations provide insights into the processes of star formation and evolution. In a sense, these ancient stellar cities are cosmic time capsules, preserving the history of the universe within their luminous bounds. Their enduring presence in the night sky is a reminder of the cosmos' vast age and the enduring mysteries that lie within. The celestial chronometers, age determination. Globular clusters, those ancient stellar cities suspended in the halo of our galaxy, are among the oldest objects in the universe. Their age, a testament to their endurance, can be determined through a fascinating interplay of stellar evolution and precise observation. At the heart of this process lies the study of their constituent stars, particularly the oldest and most abundant, the red giants. By measuring the light from these stars and comparing it to theoretical models, astronomers can infer their ages. This is possible because the brightness and color of stars change predictably over time, serving as a cosmic clock. The oldest globular clusters, like M92, are estimated to be around 13 billion years old, making them relics from a time when the universe was young. The determination of a globular cluster's age is not a straightforward task. It involves a deep understanding of stellar evolution, as well as meticulous observations using ground-based and space telescopes. One of the key methods is main sequence photometry, which involves measuring the luminosity and color of stars in the cluster. By plotting these measurements on a Hertzsprung-Russell diagram, astronomers can identify the main sequence turn-off point, where stars begin to evolve off the main sequence. The fainter this turn-off point, the older the cluster. This method, however, is limited by the need for extremely precise photometry, especially for older clusters where the turn-off point is very faint. Another method to determine the age of globular clusters is through the study of their horizontal branch stars. These stars, which have completed the red giant phase and are burning helium in their cores, provide a unique window into the cluster's age. The morphology of the horizontal branch, particularly the presence or absence of a blue horizontal branch, can indicate the cluster's age and metallicity. Additionally, the study of white dwarfs in globular clusters can provide age estimates, as these remnants of dead stars cool at a predictable rate. However, this method is challenging due to the faintness of white dwarfs and the need for deep, high-resolution observations. The age of globular clusters is not just a number. It is a story of endurance and resilience. These ancient stellar cities have witnessed the birth and death of stars, the formation of galaxies, and the evolution of the universe itself. They are like celestial chronometers, ticking away the seconds of cosmic time. Their study not only sheds light on the age of the universe, but also provides insights into the processes of star formation and galactic evolution. In the grand tapestry of the cosmos, globular clusters stand as enduring monuments to the passage of time. The celestial alchemists, chemical composition, globular clusters, those ancient stellar cities suspended in the halo of our galaxy, are more than just collections of stars. They are cosmic time capsules, preserving the chemical fingerprints of the early universe. Their stars, born in a single prolific burst of activity, share a remarkable uniformity in their chemical composition, a testament to their shared ancestry. Yet, within this homogeneity, subtle variations whisper tales of complex nucleosynthetic processes and the enduring dance of stellar evolution. The stars in globular clusters are predominantly old, their light carrying the spectral signatures of a time when the universe was young. They are enriched with elements heavier than hydrogen and helium, the products of stellar alchemy from even earlier generations of stars. This enrichment is not uniform, however. Some stars in these clusters exhibit anomalies, with variations in their oxygen, sodium, magnesium, and aluminum content. These chemical peculiarities are thought to arise from the cluster's self-enrichment processes, where the first generations of stars seeded the interstellar medium with heavier elements, which were then incorporated into the next generations. One of the most fascinating aspects of globular cluster chemistry is the presence of multiple stellar populations. These populations, identified through their distinct light element abundances, suggest that globular clusters experienced complex formation histories. Some models propose that these clusters formed in two distinct phases, with the second generation of stars forming from the ejecta of the first. This would explain the observed chemical variations and the presence of multiple populations. The exact mechanisms behind this process, however, remain a topic of ongoing research and debate. The enduring nature of globular clusters makes them invaluable laboratories for studying stellar evolution and nucleosynthesis. Their stars, having lived for billions of years, provide a snapshot of the chemical evolution of the universe. By studying their chemical compositions, astronomers can piece together the history of these ancient stellar cities and gain insights into the processes that shape the cosmos. Moreover, The extreme conditions within globular clusters, with their high stellar densities and close encounters, offer a unique environment for studying stellar dynamics and interactions. In this way, globular clusters continue to reveal the secrets of the universe, their ancient light guiding our understanding of the cosmos. The celestial architects, morphology and classification. Globular clusters, those ancient stellar cities, are among the oldest inhabitants of our galaxy. They are densely packed collections of stars, gravitationally bound, that orbit around the galactic core like loyal sentinels. Their morphology is as captivating as their history. These spherical or slightly elliptical formations can contain anywhere from tens of thousands to millions of stars, all huddled together in a region of space, typically just a few dozen light-years across. The stars within these clusters are often remarkably similar in age and composition, a testament to their shared origin, born in a single, monumental burst of star formation eons ago. The classification of globular clusters is a fascinating endeavor, with astronomers employing various schemes to categorize these celestial marvels. One such method is based on their concentration, ranging from class 1st, the most concentrated, to class 12th, the least. This classification reflects the density of stars near the cluster's core. For instance, Omega Centauri, one of the most massive globular clusters in the Milky Way, is a class 5th, boasting a dense core and a vast, sprawling halo of stars. Another classification system is based on the metallicity of the stars, which refers to the abundance of elements heavier than hydrogen and helium. This can provide insights into the cluster's age and the environment in which it formed. The endurance of globular clusters is a testament to their robustness. They have survived for billions of years, enduring the gravitational tugs and pulls of their galactic environment. Their stars, tightly bound by gravity, move in a complex dance, their orbits influenced by the collective gravity of their neighbors. This dynamic interplay can lead to some intriguing phenomena. For example, in the dense cores of some clusters, stars can collide or merge, giving birth to exotic objects like blue stragglers, stars that appear younger and bluer than their counterparts, defying the cluster's age. These celestial architects, with their intricate structures and enduring nature, offer a window into the past, a glimpse of the early universe and the processes that shaped the galaxies we see today. The celestial historians. Evolution of globular clusters. Globular clusters, those ancient stellar cities, are among the oldest inhabitants of our universe. They are densely packed collections of stars, gravitationally bound, that orbit around the core of a galaxy. Their age is staggering, often exceeding 10 billion years, making them relics of the early universe. These clusters are like celestial historians, preserving the stories of the cosmos' formative years. Their stars, born in a single burst of activity, share similar ages and compositions, offering a snapshot of the universe's past. The evolution of globular clusters is a tale of endurance and resilience. Born in the tumultuous early universe, they have weathered cosmic storms and galactic collisions. Their dense cores and strong gravitational bonds have allowed them to maintain their structure over eons. Yet, they are not static. Stars within them evolve, die, and sometimes explode as supernovae, enriching the cluster with heavier elements. This process, known as self-enrichment, adds layers to their history, much like rings in a tree. One fascinating aspect of globular clusters is their role in galactic evolution. They are often found orbiting the centers of galaxies, including our own Milky Way. Some theories suggest that these clusters may be the remnants of smaller galaxies that were consumed by larger ones. This makes them not just historians, but also witnesses to the growth and evolution of galaxies. Their study provides insights into the hierarchical merging process that built up the galaxies we see today. Intriguingly, globular clusters are not uniform. They exhibit variations in their stellar populations and chemical compositions. Some clusters host multiple stellar populations, with stars of different ages and compositions. This complexity challenges our understanding of their formation and evolution. It's like finding different chapters in a book, each telling a slightly different story. These variations are crucial for astronomers, as they offer clues about the conditions in the early universe and the processes that shaped these ancient stellar cities. The celestial nomads, migration and distribution. Globular clusters, those ancient stellar cities, are among the oldest inhabitants of our galaxy. They are tightly bound groups of stars, orbiting around the core of a galaxy. Their migration patterns and distribution tell a story of endurance and resilience, a testament to their ancient origins. These celestial nomads are not uniformly distributed. Instead, they are concentrated in the galactic halo, a spherical region surrounding the galactic disk. Their distribution is a relic of the early universe, a snapshot of the galaxy's formative years. The Milky Way, for instance, hosts around 150 globular clusters, each containing tens of thousands to millions of stars. Their orbits are highly elliptical and inclined, taking them on vast journeys through the galaxy. The age of globular clusters is astonishing. They are often considered fossils from the early universe, with ages ranging from 10 to 13 billion years. This makes them some of the oldest stellar systems in existence. Their endurance is a marvel of nature. They have witnessed the birth and death of stars, the formation of planets, and the evolution of galaxies. Despite the harsh conditions of space, they have managed to maintain their structure and composition. This resilience is a testament to the strength of their gravitational bonds. The stars within them are tightly packed, with distances between them much smaller than in the solar neighborhood. This close proximity leads to a high rate of stellar interactions, which can result in the formation of exotic objects like blue stragglers and millisecond pulsars. The migration of globular clusters is a complex dance, influenced by the gravitational pull of the galaxy and other massive objects. Their orbits can be highly eccentric, taking them from the galactic center to the outer halo and back again. This migration can lead to the exchange of stars between clusters and the galaxy. Some stars may be stripped from the cluster, while others may be captured. This process can significantly alter the cluster's structure and composition. The distribution of globular clusters can also provide insights into the formation and evolution of the galaxy. For example, the presence of a large number of clusters in a particular region may indicate a past merger event. The study of globular clusters, therefore, offers a unique window into the past, allowing us to understand the history and evolution of our galaxy. The celestial sentinels, globular clusters as galactic halo probes. Globular clusters, ancient stellar cities that have endured for billions of years, are scattered throughout the halo of our Milky Way galaxy. These celestial sentinels, with their dense concentrations of stars, serve as invaluable probes into the distant past and the very fabric of our galactic neighborhood. Their enduring nature offers a window into the early universe, providing insights into the processes that shaped galaxies and the cosmos as we know them. Among the most ancient objects in the universe, globular clusters are like time capsules, preserving the conditions and compositions of the early universe. Their stars, born in a single burst of star formation, share a common age and composition, making them ideal laboratories for studying stellar evolution and the history of the Milky Way. The galactic halo, a vast and sparse region surrounding the Milky Way's disk, is home to these ancient clusters. Their orbits, often highly elliptical and inclined, carry them through the galaxy, probing its gravitational field and revealing its structure. These celestial sentinels act as tracers, mapping the distribution of dark matter and offering clues about the galaxy's formation and evolution. Their enduring presence, resistant to the tidal forces that disrupt other stellar systems, makes them reliable markers for studying the galaxy's dynamics. The metal-poor nature of globular clusters, a testament to their ancient origins, provides a stark contrast to the younger, metal-rich stars of the galactic disk. This contrast offers astronomers a unique opportunity to study the chemical evolution of the Milky Way. One of the most fascinating aspects of globular clusters is their remarkable longevity. These stellar cities have survived for billions of years, enduring the relentless pull of tidal forces and the explosive energies of stellar evolution. Their dense cores, where stars are packed tightly together, are sites of intense gravitational interactions and stellar collisions. These dynamic environments give rise to exotic objects like blue stragglers, millisecond pulsars, and low-mass 10th-ray binaries. The study of these phenomena provides valuable insights into the extreme conditions that shape the lives of stars. Moreover, the age of globular clusters, determined through precise measurements of their stellar populations, offers a lower limit on the age of the universe itself. The enduring nature of globular clusters also makes them ideal targets for studying the processes that drive stellar evolution. Their simple stellar populations, composed of stars born at the same time from the same material, provide a clean canvas for testing theories of stellar structure and evolution. By comparing the properties of stars in globular clusters with those in other environments, astronomers can unravel the complex web of factors that influence the lives of stars. Furthermore, the study of globular clusters has led to the discovery of multiple stellar populations within some clusters, challenging our understanding of star formation and cluster evolution. These findings have sparked a renewed interest in the study of globular clusters and their role in galactic evolution. The celestial storytellers, globular clusters, and galactic evolution. In the vast, velvet expanse of the night sky, ancient stellar cities quietly orbit the galactic core, their secrets whispered in the language of light. These are the globular clusters, spherical conglomerations of stars that dance in harmony, bound by gravity's invisible threads. Their age is staggering, with some estimated to be nearly as old as the universe itself, making them some of the earliest witnesses to the cosmos' grand narrative. Among the most ancient is M92, a cluster in the constellation Hercules, whose stars are believed to have formed around the same time as the Milky Way itself. These celestial time capsules offer a glimpse into the past, their stars acting as celestial storytellers, narrating the tale of galactic evolution. Each star in a globular cluster is a character in this cosmic drama, their lives intertwined and influenced by their close-knit community. Unlike the younger, more rebellious stars in the galactic disk, these ancient stars move in unison, their orbits synchronized by the cluster's immense gravitational pull. This unity has allowed them to endure for billions of years, their resilience a testament to the power of cohesion. Yet, their endurance is not without challenges. Stellar collisions and near misses are common in these densely populated stellar cities, leading to the formation of exotic objects like blue stragglers, stars that appear younger than their neighbors, having gained new life through stellar cannibalism. The stories told by these ancient clusters are not just about their own lives, but also about the galaxies that host them. Globular clusters are often found orbiting the centers of galaxies, their paths tracing the history of galactic evolution. They are the remnants of the building blocks that merged to form the galaxies we see today. For instance, the Milky Way's own globular clusters, like Omega Centauri, are thought to be the cores of dwarf galaxies that were consumed by our own. These clusters, therefore, are not just witnesses to galactic evolution but active participants, their stars contributing to the chemical enrichment of their host galaxies. Moreover, the study of globular clusters has led to fascinating discoveries about the universe's fundamental properties. For example, the observation of pulsars in the globular cluster 47 Tucanae has provided insights into the behavior of matter in extreme gravitational fields. Meanwhile, the study of globular clusters in the Fornax dwarf galaxy has challenged our understanding of dark matter, the mysterious substance that makes up a significant portion of the universe's mass. Thus, these ancient stellar cities continue to captivate astronomers, their stories offering clues to some of the universe's most profound mysteries. The celestial timekeepers, pulsars, and 10th-ray sources. In the vast, velvet expanse of the cosmos, globular clusters stand as ancient stellar cities, their stars bound together by gravity, whispering secrets of the universe's dawn. Among these ancient congregations, pulsars and 10th-ray sources serve as celestial timekeepers, their rhythmic pulses and energetic emissions offering insights into the passage of time and the nature of matter. Pulsars, the lighthouses of the universe, are the remnants of massive stars that have collapsed into incredibly dense neutron stars. They spin rapidly, emitting beams of electromagnetic radiation that sweep through space like cosmic searchlights. The oldest known pulsars and globular clusters have been ticking away for billions of years, their precision rivaling that of atomic clocks. Their endurance is a testament to the unyielding laws of physics, a steady drumbeat echoing through the eons. Within these ancient clusters, 10th-ray sources add another layer to the celestial symphony. These sources often arise from binary systems, where a neutron star or black hole strips material from a companion star, heating the stolen matter to incredible temperatures and emitting 10th rays. The age of these systems can be traced back to the cluster's formation, making them living fossils of the early universe. Some of these 10th-ray sources exhibit fascinating behavior, such as 10th-ray bursts or quasi-periodic oscillations, providing astronomers with a wealth of data to unravel the mysteries of extreme physics. The endurance of these systems, surviving for billions of years, speaks volumes about the resilience of the cosmos. The trivia surrounding these celestial timekeepers is as captivating as the phenomena themselves. For instance, some pulsars and globular clusters exhibit unusual properties, such as being part of binary systems with other neutron stars or even white dwarfs. These exotic pairings offer unique laboratories for studying the fundamental forces of nature. Moreover, the density of stars in globular clusters increases the likelihood of stellar interactions, leading to the formation of unusual objects like millisecond pulsars, which spin hundreds of times per second. The discovery of these objects has challenged and refined our understanding of stellar evolution and the behavior of matter under extreme conditions. In the grand tapestry of the cosmos, these ancient stellar cities and their celestial timekeepers continue to illuminate the dark, offering glimpses into the universe's past and the enduring laws that govern it. The celestial enigmas, blue straggler stars. In the vast, ancient cities of stars known as globular clusters, a peculiar breed of celestial bodies defies the usual rules of stellar evolution. These are the blue straggler stars, cosmic enigmas that seem to have outlived their peers, enduring long after their siblings have faded into obscurity. Globular clusters are among the oldest structures in the universe, their stars born in a frenzy of creation billions of years ago. Yet, amidst the sea of aging, red giants, these blue stragglers shine with the vigor of youth. Their blue hues a stark contrast to the expected monotony of old age. The secret to their longevity lies in their unusual formation. While most stars in a globular cluster form simultaneously and age together, blue stragglers buck this trend. They are thought to form through stellar collisions or by siphoning material from neighboring stars. This extra fuel allows them to burn brighter and hotter, defying the inevitable fade into red giants. It's as if, in a city of elderly citizens, a few individuals have discovered the fountain of youth, their vitality a testament to the dynamic and often violent nature of stellar evolution. One fascinating trivia about blue stragglers is their role in unraveling the mysteries of stellar dynamics. Their presence challenges our understanding of stellar evolution and cluster dynamics. By studying these enigmatic stars, astronomers gain insights into the complex interactions that occur within the dense cores of globular clusters. For instance, in the cluster M30, blue stragglers are found in the core, suggesting that their formation is linked to the high stellar density in these regions. This cluster, like many others, is a relic from the early universe, its stars providing a window into the past. Moreover, blue stragglers are not just cosmic oddities. They are also valuable tools for astronomers. Their unique properties allow scientists to probe the dynamics of globular clusters, shedding light on the processes that govern these ancient stellar cities. For example, the study of blue stragglers in the Cluster 47 Tucanae has revealed intricate details about the cluster's structure and evolution. This cluster, visible from the southern hemisphere, is one of the most massive and luminous globular clusters in the Milky Way. Its blue stragglers, scattered throughout its dense core, offer a glimpse into the turbulent history of this stellar metropolis. The celestial riddles, millisecond pulsars. In the vast, velvet expanse of the cosmos, globular clusters stand as ancient stellar cities, their stars bound together by gravity, whispering secrets of the universe's earliest days. Among these celestial elders, millisecond pulsars spin like cosmic ballerinas, Their rapid rotations a testament to the endurance and age of these stellar remnants. These enigmatic objects are neutron stars, the ultra-dense cores of once massive stars, now spinning hundreds of times per second. Their name, millisecond pulsars, comes from their incredibly fast rotational periods, some completing a full rotation in just a few milliseconds. The formation of millisecond pulsars is a cosmic dance of death and rebirth. They are born from binary star systems within globular clusters, where a neutron star feeds on the outer layers of a companion star. This accretion of material spins up the neutron star, transforming it into a millisecond pulsar. The process is a remarkable example of stellar recycling, where the death of one star breathes new life into another. These pulsars are nature's most precise clocks, their pulses as regular as atomic clocks. This precision makes them invaluable tools for astronomers, allowing them to study gravitational waves, the interstellar medium, and even the very fabric of spacetime. In the dense environment of globular clusters, millisecond pulsars are surprisingly common. In fact, some clusters are veritable pulsar factories, with dozens or even hundreds of these objects spinning in their hearts. The globular cluster 47 Tucanae, for instance, is home to at least 23 known millisecond pulsars. This abundance is a result of the cluster's high stellar density, which increases the likelihood of binary star systems and, consequently, the formation of millisecond pulsars. The study of these objects provides a window into the past, offering insights into the early universe and the processes that shaped it. The endurance of millisecond pulsars is a marvel of the cosmos. They have been spinning for billions of years, their rotation slowed only slightly by the resistance of the interstellar medium. This makes them some of the oldest and most long-lived objects in the universe. Their study not only sheds light on the past, but also helps us understand the future of our own star, the Sun. For in the distant future, the Sun too may end its life as a neutron star, perhaps even a millisecond pulsar, spinning in the heart of a globular cluster, a testament to the enduring dance of stars. The celestial mysteries, intermediate mass black holes. In the vast, velvet expanse of the cosmos, globular clusters stand as ancient stellar cities, their twinkling inhabitants bound together by gravity and time. These spherical conglomerations of stars, often as old as the universe itself, hold secrets that have perplexed astronomers for generations. Among these enigmas are intermediate mass black holes, celestial behemoths that lurk at the hearts of these stellar metropolises, their presence hinted at through the peculiar dance of stars around them. These black holes, with masses ranging from 100 to several thousand times that of our Sun, are the middleweights of the black hole family, their origins and evolution as mysterious as the clusters they inhabit. The age and endurance of globular clusters are nothing short of astonishing. They are among the oldest structures in the universe, their stars forged in the fiery crucible of the early cosmos. These ancient stellar cities have witnessed the birth and death of generations of stars, their gravitational embrace keeping their stellar inhabitants close, like a cosmic family album. The stars within them are often older than the universe's disk galaxies, making them veritable time capsules, preserving the conditions and compositions of the early universe. Their endurance is a testament to their resilience, having survived galactic collisions, mergers, and the relentless march of time. Intermediate mass black holes, the celestial mysteries at the hearts of these ancient clusters, are thought to be the seeds from which supermassive black holes grow. Yet, their formation and evolution remain shrouded in uncertainty. Some theories suggest they form from the merger of smaller black holes, while others propose they are the remnants of massive stars that once shone brightly within these clusters. Their presence is often inferred through the high velocities of stars near the cluster's core, a gravitational ballet choreographed by the invisible hand of the black hole. In some cases, the sudden brightening of a star, a telltale sign of a tidal disruption event, betrays the black hole's otherwise hidden nature. The study of these enigmatic objects is fraught with challenges. Their elusive nature and the dense stellar environments in which they reside make them difficult to observe directly. However, advances in observational technology and theoretical modeling are shedding new light on these cosmic enigmas. For instance, The detection of gravitational waves from merging black holes has opened a new window into the universe, allowing astronomers to probe the dark hearts of globular clusters in unprecedented detail. Moreover, the study of these intermediate-mass black holes offers insights into the formation and evolution of supermassive black holes, the cosmic leviathans that reside at the centers of galaxies. In this way, the ancient stellar cities of globular clusters continue to reveal the secrets of the cosmos, their enduring presence a testament to the enduring mystery and majesty of the universe. The celestial puzzles, multiple stellar populations, globular clusters, those ancient stellar cities suspended in the velvet canvas of the night sky, have long been a subject of fascination for astronomers. Among their many mysteries, the phenomenon of multiple stellar populations stands out as a particularly intriguing puzzle. These clusters, some of the oldest objects in the universe, are teeming with stars that can be broadly categorized into two distinct groups: the original, ancient population and a younger, slightly enriched population. The existence of these multiple populations challenges our understanding of star formation and the evolution of these celestial giants. The ancient stars in globular clusters are typically metal-poor, meaning they contain fewer heavy elements than stars like our Sun. This is a telltale sign of their antiquity, as they formed from the pristine material left over from the Big Bang. However, the younger population of stars exhibits a higher metallicity, indicating that they formed from gas that had been enriched by previous generations of stars. This enrichment process is a complex interplay of stellar winds, supernovae, and the gravitational dynamics within the cluster. The exact mechanisms that allow for this second generation of stars to form remain a topic of ongoing research. One of the most fascinating aspects of multiple stellar populations is their distribution within globular clusters. In many clusters, the younger, more metal-rich stars are often found in the central regions, while the older, metal-poor stars are more dispersed throughout the cluster. This segregation suggests that the younger stars may have formed from the gas that was concentrated in the core of the cluster. The gravitational pull of the older stars could have drawn in the enriched gas, leading to the formation of new stars in the heart of the cluster. This process not only highlights the dynamic nature of globular clusters, but also underscores their role as living, evolving entities. The study of multiple stellar populations in globular clusters is not just an academic exercise. It has practical implications for our understanding of galaxy formation and evolution. Globular clusters are often considered the building blocks of galaxies, and their properties can provide insights into the early universe. By unraveling the mysteries of multiple stellar populations, astronomers hope to gain a deeper understanding of the processes that shape the cosmos. The enduring nature of these stellar cities, with their complex histories and intricate dynamics, continues to captivate and inspire, offering a window into the ancient past and a glimpse into the future of stellar evolution. The celestial conundrums, dark matter and globular clusters. Globular clusters, those ancient stellar cities, are among the oldest inhabitants of our universe. They are tightly bound groups of stars, orbiting around a galactic core like loyal subjects to a king. Their age is staggering, with some estimated to be nearly as old as the universe itself. These celestial bodies have endured for billions of years, silently witnessing the cosmic dance of galaxies and stars. Their endurance is a testament to their robustness, a quality that has made them invaluable to astronomers studying the mysteries of the cosmos. One of the most intriguing conundrums surrounding globular clusters is their relationship with dark matter. Dark matter, an invisible and enigmatic substance, is thought to make up a significant portion of the universe's mass. Its presence is inferred through gravitational effects on visible matter, such as stars and galaxies. Globular clusters, with their high stellar densities and ancient origins, provide a unique laboratory for studying the influence of dark matter. Some theories suggest that dark matter halos, vast regions of dark matter surrounding galaxies, may have played a crucial role in the formation and evolution of globular clusters. The gravitational pull of these halos could have helped bind stars together, creating the tightly packed clusters we observe today. The interplay between dark matter and globular clusters is not without its controversies. Some studies have suggested that the presence of dark matter within globular clusters could explain certain observed phenomena, such as the high velocities of stars within these clusters. However, other research has challenged this idea, proposing alternative explanations for these observations. The debate is far from settled, and the mystery of dark matter's role in globular clusters continues to captivate astronomers. This celestial conundrum is a reminder of the many unanswered questions that still lurk in the shadows of our universe. In the grand tapestry of the cosmos, globular clusters stand as ancient sentinels, their stories etched in the stars. They are more than just collections of stars. They are living fossils that offer a glimpse into the early universe. Their enduring presence and complex relationship with dark matter make them a fascinating subject of study. As we continue to unravel the mysteries of these stellar cities, we inch closer to understanding the very fabric of our universe. The journey is long, and the answers are not always clear, but the quest to understand these celestial conundrums is a testament to human curiosity and our enduring fascination with the night sky. The celestial horizons, future research and discoveries. Globular clusters, those ancient stellar cities, have long captivated astronomers with their dense concentrations of stars, all bound together by gravity. These celestial bodies are among the oldest objects in the universe, with ages spanning up to 13 billion years. Their endurance is a testament to their resilience, having weathered the tumultuous early years of the cosmos. As we gaze into the future of astronomical research, these clusters promise to reveal even more about the origins and evolution of galaxies, including our own Milky Way. One of the most intriguing aspects of globular clusters is their potential to harbor exotic objects, such as black holes and neutron stars. These remnants of massive stars offer a unique window into the extreme physics that governs the universe. Future research aims to detect and study these elusive objects within the dense cores of globular clusters. Advanced telescopes and gravitational wave detectors, like LIGO, are poised to uncover the secrets of these hidden inhabitants, providing insights into the life cycles of stars and the nature of gravity itself. The study of globular clusters also holds promise for understanding the distribution of dark matter, the mysterious substance that permeates the cosmos. These ancient stellar systems are believed to be embedded within halos of dark matter, which exert a gravitational influence on the visible stars. By mapping the motions of stars within globular clusters, astronomers can infer the presence and distribution of dark matter. This line of research could shed light on one of the most profound mysteries in astrophysics, bringing us closer to comprehending the fabric of the universe. Moreover, the future of globular cluster research is intertwined with the exploration of exoplanets. Recent discoveries have shown that planets can form in the dense environments of globular clusters, challenging previous assumptions about planet formation. Studying these exotic planetary systems can provide valuable insights into the conditions necessary for planet formation and the potential for life in extreme environments. As our understanding of globular clusters deepens, so too does our appreciation for the diversity and resilience of the cosmos. The celestial legacy, globular clusters in human culture. Globular clusters, those ancient stellar cities, have been silent witnesses to the cosmos' grand tapestry for billions of years. Their enduring presence has left an indelible mark on human culture, inspiring awe and curiosity across generations. These dense collections of stars, bound together by gravity, have been a source of fascination, often intertwined with myths, legends, and scientific exploration. Their age, often exceeding 10 billion years, makes them some of the oldest inhabitants of our universe, offering a glimpse into the early epochs of cosmic history. In many cultures, these celestial bodies have been seen as omens or symbols of eternity. For instance, the ancient Greeks and Romans associated them with the mythological figures and deities, seeing in their unchanging nature a reflection of divine order. The cluster Omega Centauri, visible from the southern hemisphere, was once thought to be a portal to other worlds in some indigenous Australian traditions. Its enduring presence in the night sky, a constant amidst the ever-changing celestial landscape, made it a powerful symbol in their storytelling and navigation. The sheer age of these clusters, far outdating human civilization, adds a layer of mystique, making them timeless symbols of endurance and constancy. The scientific study of globular clusters has also left a profound impact on human culture. The realization that these clusters are relics from the early universe has driven astronomers to study them intensely, seeking clues about the cosmos' formation and evolution. The discovery of pulsars in the globular cluster 47 Tucanae, for example, revolutionized our understanding of neutron stars and their behavior. This cluster, visible from the southern skies, became a focal point for astronomers, its ancient stars offering insights into the fundamental workings of the universe. The cultural significance of these findings extends beyond the scientific community, inspiring art, literature, and public engagement with astronomy. Moreover, globular clusters have played a role in shaping our understanding of our place in the universe. The realization that our Milky Way galaxy is surrounded by a halo of these ancient clusters has humbled humanity, emphasizing the vastness and age of the cosmos. This perspective has influenced philosophical and spiritual thoughts, prompting reflections on the nature of existence and our connection to the universe. The enduring presence of these stellar cities, their lights traveling across billions of years to reach our eyes, serves as a reminder of the cosmos' grandeur and our small, yet significant role within it. As we draw our journey to a close, let's take a moment to marvel at the ancient stellar cities that are globular clusters. These are not merely clusters of stars. They are time capsules, each containing stars that have been shining together for over 10 billion years. They are the enduring sentinels of our galaxy, silent witnesses to the unfolding drama of the cosmos. Imagine, if you will, the stories these clusters could tell. They've watched as galaxies danced and collided, as stars were born and died, and as the universe itself continued to expand and evolve. They are the granddaddies of the cosmos, the original cities of stars that have stood the test of time. Here's a fascinating tidbit to leave you with. Some of these ancient clusters are so dense that if you were to stand on a hypothetical planet within one, the night sky would be ablaze with the light of millions of stars, each one a sun in its own right. It would be a sight to behold, a testament to the enduring beauty and majesty of these ancient stellar cities. As we sign off, we hope you've enjoyed this journey through time and space. We invite you to join us again for our next cosmic adventure. Until then, keep looking up, keep wondering, and keep exploring. The universe is vast and full of wonders, and there's always more to discover. So, until our next journey, this is your cosmic guide signing off. Clear skies and happy stargazing.